So section 3.4, directed acyclic graphs, is the last section in our graph theory unit, and it starts off with a question about chickens and their pecking order. So pecking order is a term that's used to describe how chickens can kind of assert dominance amongst each other and determine which one is the best chicken, I guess, or something like that. So if we have a scenario like this where we know that chicken A pecks chickens B and E and B pecks chicken C, etc., we can represent this in a graph where naturally each chicken is a vertex. And we can draw an arrow if one chicken pecks another. So A pecks B, so we would draw an edge from A to B, but we want to be specific here because chicken A pecks chicken B, but not the other way around. And so we really need to give some sort of a direction here to indicate who is pecking who. So A pecks B, so we're going to do an arrow from A to B. Similarly, we'll do an arrow from A to E. Okay, then we have that chicken B pecks chicken C. C pecks D and E. D pecks E, and E pecks nobody, right? So we end up with this graph with this extra little bit of information where we put an arrow on each one of our edges to indicate a direction here. And so sort of looking at this graph, it becomes clear that in some way chicken A is sort of the head of this whole thing. Whoops, I shouldn't. Okay. Chicken A is sort of the most important one, because he doesn't necessarily peck all of the other chickens, but nobody is pecking him. So there's that. I guess it's a chicken, so it's maybe a her. Nobody is pecking A. And even though A doesn't, for example, peck C or D directly, A pecks B and then B pecks C, or A pecks B and then B pecks C and then C pecks D. So in this sense, A is sort of in charge of the whole thing, even though they're not directly pecking everyone else. So we'll see that we have a specific term to describe that relationship in a little bit. All right, question 2 has to do with the Netflix movie Bandersnatch, which was very topical when I wrote this problem a year and a half ago. And this is a sort of choose your own adventure movie where you start watching and then all of a sudden the movie pauses and it tells you can make a choice here. You can either choose to get up or sleep in, or you can choose to eat this cereal or that cereal, or you can choose to walk or take the bus. There's all these various different choices, and it leads you to other scenarios and other choices. And so the question that I asked is, the people making this movie, could they set up the movie so that you have a never-ending movie? And the answer, of course, is yeah, right? They could do that, and in fact, I think maybe they do that, where you have some sort of starting position where the movie begins, and then you reach a certain part where you have two different options. Let's say, you know, eat this cereal for breakfast or this other cereal for breakfast. And from there, maybe these branch into other choices. Maybe sometimes they even branch to the same choice. Maybe no matter what cereal you choose, eventually you have the option to go here. Or not, but the only way to make it so that the movie goes on forever is to eventually set up some kind of a loop here, where making some specific set of choices leads you to a place where you can make another choice, or you can make the choice to go back to some earlier phase. Right? If we had a situation like this, then you could, you know, come here, make choice B, whatever that choice is, make choice B again, and then make choice B again, and you're back to the starting place. If you keep making that same choice over and over again, you're kind of stuck in this infinite loop. So yes, you can, or the movie maker could set it up like this, and maybe does. And finally, the question 3 in the warm-up has to do with the power set of A, and in case we've forgotten, remember, the power set of A is just the set of all subsets of a particular set A. And we said that A is the set containing little a, little b, and little c. So the power set of A is all the subsets of this set. And we know that that's going to include the empty set. It's also going to include just A, just B, and just C. I'm sort of suggestively drawing this in a way where I'm organizing the sets based on how big they are. And then we've got AB, we've got AC, we've got BC, And finally, we've got the subset consisting of the entire set A itself, which is little a, little b, little c. Okay, so I can turn this into a graph then, where each subset is its own vertex, and then we want some kind of relationship between them. So what would be a natural relationship here? Well, these are all maybe subsets of each other, or some of them are subsets of each other. The empty set is a subset of everything. So maybe what I'll do is just put an arrow if one set is a subset of another. So the empty set is a subset of A and B and C. It's also a subset of these as well, but I don't want my graph to get too messy, so maybe I'll just say it's a subset and this is not a subset. Okay, well, this is the smallest subset that the empty set is a subset of in terms of cardinality. Okay, similarly, the subset A is a subset of AB and a subset of AC. B is a subset of AB and a subset of BC, and C is a subset of AC and BC. And these three subsets are all a subset of ABC. Okay, so we can draw a directed graph that looks like this. If you squint a little, this kind of looks like a cube. In math, we call this a partially ordered set because it's ordered in some particular way where some sets are sort of below other sets and other subsets of them, but it's not necessarily the case that any two vertices can be compared to each other. Like A and B aren't subsets of each other, so it's only partially ordered. Okay, but this diagram is sort of a natural way of representing this relationship here. And so directed graphs really do come up in many different contexts, but most frequently you can really kind of think about them as some kind of a flow chart. I don't know if you heard that noise, but that just means that the cat has ruined something downstairs. Okay. So let's move on to some definitions here. We say that a directed graph is an ordered pair, right? Just like a graph, it's a set of vertices and a set of edges, except we're going to specify that that set of edges is actually a directed set of edges, which consists of ordered pairs of vertices as opposed to subsets, two-element subsets of vertices. Okay, so this is exactly what we were talking about in the warm-up. It's like a graph, except we're giving some sort of a natural direction to each of our edges, right? So this would be the graph with a vertex set, little a, little b, little c, and we'd have a directed edge set where instead of saying we have edge AB and edge AC, we want to specify that there's arrows here, there's direction involved. So instead of saying that these are two-element subsets, we'll write them as an ordered pair, A to B, and then we have another edge from A to C. So really the only difference between a regular graph and a directed graph is we put an arrow on the edges. If there's an arrow from A to B, so like we have up here, if A comma B is an element of our edge set, then we say that the edge is out of A and into B. So with directed graphs, it's harder to talk about degrees, but you can talk about in degrees or out degrees. Like in this example up here, we would say that the out degree of the vertex A is 2, because there's two edges coming out of A. But the in degree of A would be 0, because there's no edges going into A. Similarly, B and C would have an in degree of 1 each and 0 out degree. And finally, we say a directed acyclic graph is a directed graph that has no directed cycle. So it has a property that if you start at any vertex and you follow a directed path, you follow just a path along arrows, you never get back to the starting point. This graph, this simple one that I drew up here, this directed graph, this is a directed acyclic graph, because if you start at A and follow out arrows, you're never going to get back to A. If you started at B or C, you're kind of just stuck, right? You can't go anywhere because there's no out arrows coming out of B or C. So this is a really simple example of a directed acyclic graph. But that chicken example from before is also a directed acyclic graph. Now, if you ignore the arrows, this graph clearly has cycles. It's not a tree. But it doesn't have any directed cycles, right? If you start at A and follow these arrows, you're never going to get back to A. If you did, you would have a real problem with authority in your chicken coop, right? Because no one would be in charge if A pecks B and B pecks C and somehow it comes back to A again, right? So this is an example of a directed acyclic graph. You can't start at any one vertex, follow out arrows, and come back to that starting point, okay? As opposed to question 2 here, this graph here is a directed graph, but it does have a directed cycle. For example, right here, start at this vertex here, come down, come back around. This we would consider a directed cycle. So this is not a directed acyclic graph, whereas the first example is a directed acyclic graph. Acyclic means it does not have cycles, no cycles. Okay. This example down here, this is a directed acyclic graph. No matter where you start, you're always sort of traveling up this graph. You can never come back down again and complete a cycle. So this is a directed acyclic graph. Now, if your graph, right, if you ignore the direction, if you ignore the arrows on your graph, and it's a tree, then it's definitely going to be a directed acyclic graph. Right, so start with any kind of tree that you like. I don't know, something like this. Right, and then you put any kind of arrows that you want here. Doesn't even matter how you do it. If you start with a tree graph and then add arrows to make it a directed graph, it's not going to have any directed cycles because it doesn't have any cycles at all. You can never come back to any starting point because there's no cycles at all. So any tree graph, any graph that can be seen as a tree graph if you ignore the arrows, is going to be a directed acyclic graph, meaning it's not going to have any directed cycles because it doesn't have any cycles at all. But the reverse of that, the converse of that, is not true. You can have a graph that's a directed acyclic graph that's not necessarily a tree when you consider it just sort of without its directed edges, right? So this graph, if you ignore the arrows on it, it's going to have the cycle A, B, E, F, C, A, right? Ignoring the arrows, this has a cycle, which means this is not a tree. However, it is still a directed acyclic graph, because there's no directed cycles, right? If you start at A, you can never come back to A because all of your arrows are pointing down. Similarly, if you start at B, you can never come back to B. No matter where you start, if you're following out arrows, you can never come back up again. So this is a directed acyclic graph. All right, so you can be a directed acyclic graph without being a tree, but you can't be a tree without being a directed acyclic graph. Okay, and now the last definition that we want to talk about here is we say that a vertex in a graph is reachable from another vertex if you can get from one to the other by a directed path. So we would say in this one, if we want to say that vertex V is reachable from U, it doesn't mean there's a directed edge directly there, it just means you could get there possibly by going through some other path. Right, so this is an example where V is reachable from U. V is also reachable from W. You can get to V from W, in fact, directly. And so in this graph up here, every vertex in the graph is reachable from A. In other words, you could start at A and get to any other vertex in the graph through a directed path. Right, and this is important in the context, well, sort of, again, in the context of the chicken problem at the beginning. Every vertex was also reachable from A. You could get from A to B, from A to C, from A to D, and from A to E. Okay, and this is sort of just saying there's sort of one starting position where you can get to every other vertex from that starting point. Not all directed graphs will have that property. So for example, if you have a graph that looks like this, there's no one single vertex here such that every other vertex in the graph is reachable from it, right? Because, for example, you can only get, from X you can only get to Y, and from Z you can only get to Y. So there's no way for you to get from X to Z or vice versa. So if this was representing a flock of chickens, for example, there's no one chicken that's in charge here, right? Because there's no sort of dominance from X to Z or from Z to X. They're sort of, I guess, just co-bullies of the poor chicken Y. All right, but that's the idea behind reachability, and you can learn a little bit more about directed acyclic graphs in the exercises.